So today I'll talk about this technique called as Principal Component Analysis, or PCA for short. I'm sure most of you would have heard about this technique, but nevertheless, let me take you through the technicalities of this method. So just to give you an overview of the topic, the Principal Component Analysis is what we call as the Dimensionality Reduction technique. This is just one of the dimensionality reduction techniques. In fact, there is another technique called as factor analysis, and there are other techniques as well, but this is one of the most widely used dimensionality reduction technique. Okay, so essentially what it means is, when you are working with large data sets, you will have some hundreds of variables. Okay, so if you use all of the hundreds of variables when you are building your predictive model, it might not make sense. Okay, so there might be some kind of an overfitting. The accuracy might not be that great. Okay, so to make the model more accurate and more precise, out of all those hundreds of features, we take only those features which we consider as important. Okay, just to enhance the predictive power of the model. Okay, so that is why the reduction of the hundreds of variables to only those variables that make sense. So that is what we call as dimensionality reduction. Okay, you can also call it as a variable reduction. So we do this to reduce overfitting and improve accuracy in the model. So for example, in your typical normal small scale data science projects, you might not have the need to do this, employ this technique. Okay, but when you're working with large data sets, so for example, 6 years back, I was working on a data set in Kaggle. Okay, there the number of features was very high. I think it was around 176 features or something like that. But then on that dataset, I was able to apply this PCA, and then I reduced the number of features. I don't remember the final number of features, but that was what I did. And as a result of that, what happened was, I think there were around some 1,300 teams who participated in the competition. Out of that, I came out 45 or something like that. Okay, so that is the improvement in accuracy that you get when you apply this kind of a technique. Okay, so this is what gives you an edge in improving the accuracy of your predictive models. So typically, if you see, there are two methods for dimensionality reduction. Okay, so one is called as feature elimination, and the other is called as feature extraction. Now, this PCA is one of the feature extraction techniques. Okay, so feature elimination is nothing but, out of all those hundreds of variables, you identify, you take a call on what columns to drop or what variables to drop. So that is what we call as a feature elimination. Feature extraction is, you do some kind of a mathematical analysis, or you run some kind of an algorithm, and then that algorithm identifies and extracts those features which it considers to be the most valuable. So that is what we call as the feature extraction technique. Okay, so that's what we are saying here. Out of many variables, PCA identifies only the important ones. So what is the concept here? So let's say there are n independent variables. So independent variables are the predictor variables which you use to predict the value of the target variable. Right? So assume that there are n independent variables. In PCA, what we do is we create n new independent variables. Okay, and these new variables are combinations of the existing variables. And after creating these new variables, like as in combinations, we take the most important out of these new variables. So this is the core method of the principal components analysis. Okay, so what's the advantage of this technique? It does not cause a huge information loss like the feature elimination method. So for example, in the feature elimination, what you do is you just drop those variables entirely, right? But here what you do is you create combinations of all the different combinations out of those variables. So even if you drop some of the variables, since that variable is retained in some format as a combination, you do not lose all the information. Okay, so that is what we are saying, does not cause huge information loss like the feature elimination method. Why does this happen? Because new variables are the combination of existing variables, and you retain that information. Okay, but what is the disadvantage of this technique? New features are less interpretable. So what do I mean by that? So let's say you have variables like income, age, and so on, right? So directly, if you look at those variables in isolation, you look at income in isolation, you look at age in isolation, you can understand what's the meaning of those variables, right? But when you make those linear combinations out of income and age, what column you get as a result, that you cannot explain or that you cannot interpret. That is just a feature, or that is just another variable which serves to increase the predictive power of your model, but you cannot interpret it in any way. So it is basically, it's meaningless, right? From a common sense standpoint, it is meaningless. From a mathematical or scientific standpoint, it serves some purpose, but from a common sense interpretable standpoint, it is meaningless. So that is the disadvantage of this technique. So before I go to the steps and everything, are there any questions until now?
Are these new independent variables you are creating, right? So are these a replica, or few of them are combinations?
Combinations.
Only we can take few combinations, or entire the thing is a replica of already existing independent variables.
So whatever comes out of that principal component analysis will be combinations. Okay. Whatever you input into your predictive model, that is based on your choice. So you can choose either to have only what comes out of the principal component analysis, or you can choose to have something from the principal component analysis and some other independent variable separately. So that is a call that you take. That is based on that people usually do by trial and error. So first, let's say you take only those from the PCA. Okay. Then you see what the accuracy is, and then you do one more trial, including something from the other set of variables, and see how the accuracy comes out to be. So that is a call which you take when you are actually building the model. Any other questions? Okay, let me go to the next one. So this is a pictorial representation of how that algorithm works. Okay. So what we basically do here is we create some new axes, okay, that is X and Y axis, that provide the best angle to see and evaluate the data. Okay, and we do this because the difference between the observations are better visible. So let's say you have two variables X and Y. Okay, I'm just saying two variables because that is what can be visualized on a two-dimensional plane. If you have more variables, that is more than two variables, then it is called as the hyperplane, which is not so easily visualized. So just to help you understand the concept, let us take the example of two variables X and Y. Okay. Now in the original data set, this is what the coordination plot or the scatter plot looks like. Okay. Now you see these two lines here. So each dot here is a data point. Okay. Now the lines that you see here, there is one green line and one red line, right? So this is what we call as a dimensional vector. Okay, so that is something. So in a vector, if you remember in physics, you remember it is something which has a magnitude and a direction. Okay. So each of these lines is what we call as a vector. Okay. Now this is the original data set. Now you apply that PCA algorithm. What happens is it creates new axes out of the X and Y original that you have. So it creates something called as principal component 1 and principal component 2, which is something like a combination out of this X and Y. And that combination looks like this. So when you plot the data points according to those combinations, this is how the data points look like, and this is how the vectors look like. Okay. So what is the advantage of doing this? Now you see this red colored line, right? This vector is very much aligned with the direction of the data points that we have here. Okay. So just to get to this alignment, we apply this principal component analysis. Okay. So this is how the algorithm works internally. So you feed in the original data set, it applies certain operations, and then it calculates new values called as principal components, and it plots the data points according to those newly created principal components and calculates the vectors accordingly, and then takes a call on which is the best vector, or which is the principal component which is giving you the highest information gain. Okay, I will go into more details into how this works in the next slide, but this is just a pictorial representation of the process. Okay. So the steps so basically when you are doing principal component analysis, it is not necessary that you have to follow these steps one by one. Okay. The statistical software packages that we have today, such as R or Python, they already have algorithms which have these steps built in. Okay. So when you run that algorithm, these steps run one by one. Okay. So first step that we do is we standardize the data. Okay. So why do we do this? So let's say there are two variables in the data. Okay. One variable has values ranging from 0 to 100. Another variable has values ranging from 0 to 1. So when you don't standardize the data, by default, what the algorithm will do is it will assign a higher weightage to these values which range from 0 to 100. Okay, and it will assign a lower weightage to those values ranging from 0 to 1. Now assume that 0 to 100 is something like a marks and 0 to 1 is something like a percentage. Okay, or maybe 0 to 100 is an age and 0 to 1 is a percentage. Okay, so it doesn't make sense for you to give a higher weightage to the age and lower weightage to percentage. Both of those variables might be equally important, right? So that is why we do this standardization. In data science terminology or in statistical terminology, this is also called as scaling or normalization. So we bring all the data points to the same scale. So how do we do that? We use this formula. So you might have heard about this parameter. We call this as the z-score. So this z value, how you calculate is z equals that. So for each data point, you have to calculate the z value to normalize it. So that particular value minus the mean of that variable divided by the standard deviation of that variable. Okay. So this is the first step where you standardize the data. And then you build something called as the covariance matrix. Okay. So what this matrix is basically, it summarizes the correlations between all possible combinations of variables. Okay. So covariance matrix is nothing but, so let's say you have x, y, z, right? So it will calculate the covariance between x and y, and then it will calculate the covariance between y and z, and then it will calculate the covariance between x and z, and so on. Okay. And how does this do this? It uses this formula. So summation of xi minus x bar into yi minus y bar divided by n minus 1. So xi is nothing but each x variable value that you have in your data set. X bar is the average of all those x variables of the entire set of x data points. Ya is the each data point in the y variable that you have. Y bar is the average of the entire set of y. N is nothing but the total number of observations in your data set. So this is the formula for covariance between x and y. So like this, what the algorithm does is it will build this covariance matrix for all possible combinations of all variables that you have. So for example, let's say you have 100 variables in your data set, right? So the total number of covariances matrix that will be built is 100C2. So this covariance is commutative, as in covariance between x and y is the same as the covariance between y and x. Okay. So if you have 100 variables, then you will have to create 100C2 covariance matrix. So 100C2 is nothing but 100 into 99 by 1 into 2. So those many combinations you will have. Okay. So of course, so this is not possible to do it manually, and that's why we use software packages today. And then what we do is we calculate something called as eigenvectors and eigenvalues. Okay. So I don't know if you have come across these terms, but in TN state we have this in our +2 or 12th standard syllabus. So in the matrices and determinants, when we are talking about those concepts, we are also taught to calculate how to calculate the eigenvectors and eigenvalues. So this is nothing but a matrix format. Okay? So you have a matrix of values, and then you take a transpose of that matrix, and then you multiply that matrix by its transpose, and then you get a set of values. So that matrix is called as an eigenvector, and then the values inside the matrix are called as eigenvalues. Okay. So once we do this calculation, we sort by the descending order of the eigenvalues. Okay. And then we identify the principal components. So basically the vector or the variable having the highest eigenvalue is the first principal component, and then we sort it based on the descending order of the eigenvalues, and then we identify the principal components. Okay. So how do we exactly identify the principal components? we have something called as a scree plot. Okay, I'm not sure of the terminology or why they have named this plot as a scree, but this is called as a scree plot, which helps you identify what are the top contributors or top principal components in your data. Okay, so a few slides back we talked about creating n new independent variables, right? So let's say there are 10 independent variables originally in your data. Out of them we create 10 new independent variables, which are nothing but combinations of the existing variables, right? So those variables, those 10 new independent variables, are what you plot on the x-axis. Okay, so that is what we call as principal components. And for each variable, you calculate something called as the percentage of explained variance. So variable 1 explains 40% of the variance. So by variance, what do you mean? It is the variance in the target variable or the dependent variable. Okay, so are you clear until now? Any questions here in the steps? Any doubts, clarifications? Okay, we can go to the next one. So how you do this is, this percentage of explained variance is very similar to what you have in your linear regression method also. So at the end of your linear regression model, if you see, there is something called as an R square or the adjusted R square value that you take. So that is also very similar to this. That also explains the amount of variation in the target variable explained by the independent variables. So this is also the same thing. How much of the variation in the target does the first principal component explain? How much of the variation in the target does the second principal component explain? So like that, you sort these principal components in the descending order of the percentage of explained variances. Okay. So now if you see here, the principal component 1 alone is enough to explain up to 40% of the variation in the target variable. Okay. So second principal component alone is enough to explain around 15% of the variation in the target, and so on. So like this you can, so this is where you make that choice as to how many principal components do you want to have in your final data set. So you look at this graph and then you take a call whether should I have just one of them, or should I take two, should I take the first three, and so on. But this helps you prioritize those variables out of the top 100 or so variables that you have in your data set. Okay. So so at the end of this process, what you'll have is this final list of principal components, out of which you can select the top variables which you feel will enhance the predictive power of your model. Any questions?
How do we choose those new independent variables? How do we find the combination?
So that is what the algorithm basically does, right? So for example, when you say 1 here, 1 is a combination of maybe 1 and 2 or 1 and 3. We don't know. So that depends on how that algorithm runs.
Okay. So that is more the algorithm's job than our job.
Yes. So whatever steps that I mentioned here, we are not going to be doing them, and it is not possible for us to do these steps also, because when you are working with large data sets with many variables, it's just it's not feasible to manually do these calculations. So all those different combinations of variables is what the algorithm takes, and then it calculates these eigenvectors, eigenvalues, and does this sorting, and then gives you this scree plot. But that combination is what I said here when we said the new features are less interpretable, right? So for example, when we say 1 over here, 1 might be a combination of their age and percentage number. Okay, so that doesn't make any sense from a business point of view or from a common sense point of view. But just to take what is what we feel is more important statistically, we compute that principal components.
Okay,
does that answer the question?
Yeah, it does. And a combination of these principal components, it gives us what we want, right? All these principal components are a function of what we want to find. So if a function of all these principal components are there, it will give us the final result we are looking for. For example, profit. We take profit.
Yeah.
All these principal components.
So let's say, for example, you're building a model to predict the profit, right? So the target variable will be profit. Now, this profit will be dependent on, let's say, sales amount, sales quantity, the product mix, and maybe other economic factors like inflation and so on. Okay. Now, when we say principal component 1 here, that principal component 1 is a combination of two of those variables. Let's say income, average monthly income, and inflation, something like that, right? So that is something which helps you predict the profit variable.
Okay. And the percentage of explained variance. This is for what is this explained variance actually? Like,
so let's say, for example, let's take the same example, right? So the average monthly income and the inflation, right? So assume that this number 1 is a combination of average monthly income and inflation. Okay. Now this value is 40%. So what this means is average monthly income and inflation account for 40% of the variation in the sales, like that.
In the profit.
In the profit.
Profit is our target variable, right?
Target, yeah.
So the variance in the target variable.
Yes.
Okay.
So the same concept you apply in linear regression as well. When you say r square is equal to some 0.65, so it basically means that 65% of the variation in the target is accounted for by all the input variables that you have fed into the model.
Okay, understood.
Yeah. Any other questions? Okay, so that's what I had for today. I haven't gone into too much detail about how to calculate the eigenvectors and eigenvalues because I did not want to complicate the content, but if anyone is interested, please feel free to look at how exactly to calculate these matrices. Okay. But again, from a project-oriented perspective, since we have algorithms which automate this process, we don't necessarily have to bother with all the nitty-gritties of how these calculations happen. But it is important to know how the underlying mechanism works so that we will be able to use it to our best advantage. Okay. All right, so that's what I had for today.